All right, I want to talk a little bit about the Boltzmann distribution now. So we've talked about probability distributions in general and probability density functions. Now we're going to look at one. So ignore this for the time being. We're going to focus on this and then we'll do a worked example in a minute. To follow along, top of page 84, volume 3, just the top, very top, not all that junk at the bottom. So imagine we want to have a distribution function or a probability density function for the number of gas molecules per unit volume. Okay, so I'm going to call that n subscript capital V of E. It's a function of energy. So there's going to be some constant, and then this is just e to the negative e over k Boltzmann t. Remember, k Boltzmann is your, what is that, 1.381 times 10 to the minus 23 joule per Kelvin, something like that. All right, somewhere in there. You've got this constant somewhere. I don't know where I wrote it. I'm just going to double check and make sure I didn't screw that up. You know, it's probably on the back of the book. Yeah, 10 to the minus 23. Okay. And getting back to my page number so I don't screw this up. Sorry. All right. Sorry about that. Now, let's think about the units. We want this to be a probability density function, all right? And so in this case, this had better have units of something like 1 over joules, I guess, if you wanted it to be a probability density function. Now, if we want to include units on here, that's a little bit different. So in practice, what we're going to do is we're going to let this integral end up being these units here. And so in that case, we're going to want to have, if we want this to be true, if you integrate this function, we get the total number of particles over the total volume. That's going to dictate your units here. So in this case, well, let's just look at this thing. This part is no units. This part has units of joules. And this part has some constant. And then all of this junk has to equal some number per meter cubed. All right, so in this instance, well, n naught times dE will equal the number of molecules per unit volume, right? So we see that this times that increment size should give us number per unit volume. So in this case, that's going to be, let's see, n naught will be number of molecules per unit volume, times joules. So when I plug that in, this one is number of molecules over volume times joules. So we're going to get a 1 over volume times joules in order to make this give us a total number over a volume. Oh, whoops. Let's call that meters cubed. Volume is in meters cubed. So in this case, that would give you some units here. You can see that I had to think about it a little bit. In practice, how might you use this? You could talk about the number of molecules present per unit volume, perhaps as you're moving upwards in the atmosphere, right? And the energy might relate to potential energy, kinetic energy, things like that. All kinds of different things you could do. Let's now look at an example. I'll be honest with you, I don't spend a ton of time on this, but this is a good practical example of how you might use this complicated looking formula. So example 19.9, page 85, volume 3, I think that's at the top of the page. Imagine you have gas in a laser, right? And so there's some gas molecules in there. There's a bunch of different energy levels. We'll discuss energy levels at the end of the semester. There's a bunch of different energy levels. Let's say there's 2 primary energy levels where almost all of the molecules end up. So there's a high energy level and a low energy level. And the probability of gas being in other energy levels is essentially 0. So you've got some molecules, they're either going to be in the high energy state or low energy state. Those are separated by 1 electron volt, 1 eV. For reference, an eV is 1.602 times 10 to the minus 19th joules. That's the charge of an electron times a volt. Q times V is an energy in joules, and that's how much it is. All right, determine the ratio of atoms in E high to E low. So if you want to pause the video and give it a shot, go for it. This one might be a little bit crazy. I don't know, maybe you'll catch it. All right, and so what I'm going to do is I'm going to give myself some space to work. I'm going to go right about to there, and then I'm going to just check so I don't walk off the board here. Okay, that's just for my line. Okay, so what I might do is I could say, well, I don't know much other than this probability distribution. So I could say N of V in the high energy state would equal N naught EXP negative K Boltzmann T. Notice we have to use Kelvin, not Celsius, of E high. Does that fit on the page? Just barely. All right. I could write the same thing for the low energy state. Now, I don't know how many molecules there are in this gas. This seems impossible, right? And making sure that is on there, okay. But we're not trying to figure out the total number of molecules at all. We're just trying to figure out what fraction of them are in the higher energy state. One thing we could do is take a ratio of these two distribution functions. And you hear me say density function and distribution function. If you want the distinction, go read a math book or, okay. So I apologize if you're a pure mathematician and you hate me going back and forth, my bad. What happens? This parameter we have no clue about drops out. And notice we can get the ratio. I guess I should be careful. This is the number per unit volume, and this would be the number per unit volume, but the total volume will drop out. And so we can also, the number per unit volume ratio will give us the number ratio. So our requested ratio is this. And what do we get? Well, now I don't know the energy levels. I feel like I'm stuck again. But wait a minute, can I bring this exponent to the top? I can. And now, from experience, we can combine these two exponents, and rather than say E low minus E high, right, I'm going to use the fact that E low minus E high, when I combine the exponents, is equal to negative delta E. Think about that. E high minus E low, negative, gives me this result. So notice the ratio is EXP negative delta E over K Boltzmann T. And make sure that fits on the screen. It does. And then if you plug in numbers, we've got to be careful, right? You're going to have to use this conversion factor. And so delta E is equal to 1.602 times 10 to the negative 19th joules. We know K Boltzmann, we know T, you can get the answer. And I'll just write it down really quick. I have it somewhere over here. Let me just find it really quick. What did I find? 6.39 times 10 to the minus 18. That's the ratio. So the ratio is this number. And I just want to confirm that one more time. 6.39, 10 to the minus 18. So notice at room temperature, the probability of being in the higher energy state is essentially 0. Now, if you have 10 to the 23 molecules, well, a few of them are going to be up there, maybe about 1 million or so, or 100,000. So in order to get the laser to work, you might think, man, I need to pump in some energy somehow. There's optical pumping, there's electrical, there's different ways to do that. But that's how you get the population inversion, because once the atoms are up in the higher energy state, they can fall down and emit light, and you can read more about lasers. But this kind of gives you a brief introduction of how this might be useful. Okay. Let's end that video.